All right, well, welcome everyone. It's my great pleasure to introduce our Compass speaker today, Joe Prospero. So Joe joined us at Rosenstiel in 1963 from Princeton University, where he completed his Ph.D. And he's really been a pillar, not just at Rosenstiel, but within the whole atmospheric sciences community. So what he'll talk about today is essentially his career, looking at dust, most notably in Barbados, but really he's been looking at dust all over the world. So he had a series of stations pole to pole, both in the Atlantic as well as in the Pacific. And they've really provided a really unique window into not just looking at aerosols, but how aerosols have changed over the past couple of decades as a result of climate change as well as anthropogenic emissions. And what he's really also known for is having the longest observations of aerosol that we know of from the Barbados station. This is something that continues to this day. And you know, I kind of think of the records that he's generated as being the aerosol analog to the Mauna Loa station, looking at atmospheric carbon dioxide over the decades. So it's really provided us an important barometer for looking at aerosols and how they've changed over time and in space. So with that, I'd like to introduce Joe, and we'll hear more about his life chasing dust over the global oceans.
Thank you, Cassie. Thank you. Okay, good afternoon. Let me see here. This is not my laptop. Where's the page up, page down?
You use the cursor buttons here.
Oh,
To
okay.
the right and to the
Okay, good,
to the
good.
left. Yes.
Okay,
Yeah,
good.
like that.
Okay, good afternoon. So we start off with this beautiful image here. This is the Godzilla dust storm, and it's as you can see there, it's the largest dust storm that impacted on Barbados in the 60 years of record. It's the highest optical depths that were recorded on Barbados and other aeronet stations in the Caribbean. It's just a gigantic storm, attracted a lot of attention. And this shows you a few images of the storm. The red bars indicate glitter from the satellite, so you can ignore the glitter. But this is just paging through the first few days. It was a huge storm. And it got named Godzilla in a casual conversation with a scientist at NASA Goddard who said it looked like a whale. And I said, no, it's Godzilla, it's going to eat up the Caribbean. And it did. And it impacted the whole southeast United States, exceeded the PM10 standard that the EPA has for particulate air matter. And just a huge event. And one of the questions is what drives these dust events and under normal conditions and extraordinary events like that, because dust has a number of impacts. This is a busy slide. I'm not going to talk much about it, except on the right side you see aerosol dust particles. It's a strange looking dust particle, but and then it indicates I guess I can use the pointer here. Doesn't show up very well. Anyhow, it indicates on the upper right, if I have this pointer, what aerosols do. They affect the radiation. They can affect, it's an odd angle, they can affect absorption, scattering by aerosols. But from the standpoint of this, and those factors affect climate, but from the standpoint of this school, we're more interested we're additionally interested in the impact on the oceans, and part of this figure deals with the ocean issue, and it has some numbers which I highlight in squares over here. And I want to assure you that you should not take those numbers literally, because one of the topics of my talk is to show you how models are in terrible shape. There's the dispersion amongst models is order of magnitude in many cases, in some cases bigger than that. And that goes both for the amounts of dust emitted from the Earth's surface and the amount deposited to the ocean. And the other issue with the ocean is, of course, where it's deposited. And that too is a problem. It's even worse problem with model deposition of dust. And we will get to that. So this is the nicest figure you'll see because it comes from Dennis, and he showed it the other day. But it shows the regions of high nutrient, low chlorophyll, and it's extraordinary here. And there are a few other patches here, and that in the Northwest Pacific. And it's notable that the large areas of the ocean, dust doesn't mean anything, and yet it's those large areas of the ocean where most of the dust is going. So the question of the impact on HNLC areas will depend on what happens with dust in the future. But the only area where we might expect that changes will have, without extraordinary changes, would be in the Northwest Pacific Ocean. And that's, of course, Asian dust. And so what I want to do is to talk a little bit about history, because Roland has emphasized this, and this presentation is long to begin with, and this is going to make it a little longer. I'll try to trim it and space it and go over some stuff quickly. You can always see it later on the web. But I do this primarily for people, the students who are new to this area, to get some idea of the sort of stuff that I've done and what is available, from me or in general in the literature on this topic. And the different aspect of my work, my group's work, and some of them are here today, Miguel and Lillian. A significant aspect of that has been that almost from the very beginning, I've been interested in the relationship between the dust transport and climate issues, and over the years, then I developed a sense that the only way you could establish some sort of a cause-effect link is to have synoptic measurements of dust. And I started out rather early in setting up stations around the world, and we ended up with 30 or 35 stations, and you'll see that in a moment. But one of the major points I want to make is that data, which was collected mostly from, in a global sense, from the late 1960s until about 2000. When you look at models, that's the only data set that the models have to work on that's synoptic for the ocean. And the models are working with a data set where in some cases is 50 years old. So there's a real problem here for present day modeling in dealing with the ocean aspect of dust, dust emissions in general, but the dust deposition to the oceans, and how that has changed with climate, if it has changed with climate, and it has in some cases, and how it will change in the future. So I will also discuss some of the history of how I got to do what I did, but I'm not going to say much about that. Roland is specifically asked to talk about some specific characters who are important in my life, and I will do that, but I want to have to gloss through it. So how I came to be here at Miami, and it was sort of by accident. My education is before you, but my major education, my important education is my parents, even though they were uneducated. My parents were Italian immigrants. My father came here when he was in his mid-20s. He came here in 1921, was in his mid-20s, was a laborer, construction in Philadelphia, and he started a bakery in Pottstown, Pennsylvania, my hometown. The Prospero family has been bakers for generations, apparently. And my mother came over at 1960 at the age of 8 and she got a 6th grade education. My father only had a 4th grade education, but they had 3 sons who were all professionals. So that's the American dream, and they used to tell us that, get a good education because that's the only thing they can't take away from you. I didn't know who they was, but I have a better sense now of who they are. I went to a nice undergraduate college and interested in physical chemistry. I went there in 1952, 7 years after the end of the war, but 7 years into the nuclear age, became interested in things nuclear. Went to Princeton and became a nuclear chemist, a hot atom chemist, which is defined for you here from Gemini. And I had a very young professor who was interesting in a number of respects, one of which was he was the last person to lecture Einstein. Einstein would periodically ask a department at the university to send over a faculty member to update them on a recent area of research, and his job was atomic clocks. So he did atomic clocks, and Einstein died a few weeks later. No cause effect there, I don't think. So here's my Ph.D. thesis title, and about the end of my 3rd year, into my 4th year, I decided I didn't want to be a nuclear chemist the rest of my life. I could see that the area of chemistry was somewhere between regular chemistry and nuclear physics, and that middle part was fading away with the development of better instrumentation in the nuclear physics aspect. So I came to Miami as a result of that effort, of that decision, to a chance conversation with a professor of physics who invited me to a party, and he had gone to Palm Beach where he was consulting with a company, and they were working with a project at the University of Miami, and I offered some suggestions, and that's how I got my job. And the guy that hired me was Fritz Kochi, and he's very interesting from the history of this school because the school for a long time was primarily a biological fisheries, local marine geology, carbonate geology focus. And Fritz Kochi was brought in to emphasize the physical sciences, and that's what he did. He did an excellent job. And eventually he led up a division of physical sciences, which included chemistry and oceanography and meteorology, although there was not much meteorology. And he really transformed the school and started on the path it is today. So a brief note about Elizabeth Rona. You can read up about her. There's a link over here. She was here for the mid-1960s, and she was a nuclear chemist, but she worked at the laboratory. She worked primarily with uranium thorium isotopes for the geochronology of sediment cores, dating sediment cores. And she was an incredible person. She was at the very birth of the nuclear chemistry age. She worked in the laboratories of the Curies, Madame Curie and her daughter, and she knew Otto Hahn and Strassmann. She knew Heaviside, all these people. She worked with all these people, and with one of the ways that the Curies supported their operation was to make radium needles for treating tumors. They would take a thin tubing of stainless steel and put some radium in it, and they would insert that into tumors. And after a while, there would be there would be corrosion problems, perhaps, or buildup of gases, or by a number of processes. So rather than have these things leak radium, they would periodically open them up, take out the radium and the daughter isotopes, and then save the radium 226 and make another needle. But there were interesting products. One of them was polonium-210, which is a unique radionuclide in that it emits a very strong alphas, but no gammas. In 100,000 disintegrations, it'll get one gamma ray. So the nice thing is you can have a really hot source, and it emits because it emits only primarily alpha particles, essentially only alpha particles. It's easy to shield against the radiation. So they would use the polonium alpha particles to bombard beryllium films, which would then generate neutrons, which were then the neutron sources they used in the 30s in nuclear physics. So she became very prominent in developing those polonium beryllium neutron sources. She eventually had to leave Europe because, well, it was World War II was coming, and she was a Jew, and so she came to the States. She ended up with the Manhattan Project, and she was involved with the making of the triggers for the plutonium bombs, because the plutonium bomb, you needed some neutrons to initiate the process. So she was a part of that project. So she went from this initial pioneering days of radiation and isotopes to being integral to the plutonium bomb. But she never talked about she was a very reticent woman. She never talked about any of her history unless you're really proud of her, and she never mentioned the work with the plutonium. But at that time, a lot of that was classified. This was the 1960s. Cesare Emiliani was one of the prime leaders in the revival of the school, and he was a paleoclimatologist. He worked with the oxygen 16 oxygen isotope ratios in foraminifera to determine the temperature at which the foraminifera grew. So he could take sediment cores, and he would have people isolate the foraminifera according to the strata that they normally occupied in the ocean water column, and he developed the temperature scale for the ocean water column. So he made this place famous for paleo climate work. Okay, how I got into dust. Well, I was in the geophysics group, and there were a lot of people working with sediments, and particularly sediments on the Atlantic Ridge, and they would found a lot of clay materials in those sediments. But there was this paper by Pierre Bisquet, who was a graduate student at Yale, and which he looked at a couple hundred core tops from the Atlantic Ocean, and he reached the conclusion that the recent sediments had a lot of clay materials, and those were transported to the ocean either by rivers such as the Amazon or rivers in Africa, west coast of Africa. But there are no major rivers on the west coast of Africa. There's only the Senegal River, and that's a puny thing. It just hardly has anything in it. So I became interested in the possibility of atmospheric transport, and that's what got me going. And so at that time, there was a group in Barbados that was looking at aerosols on the east coast of Barbados, where it had nice exposure to the ocean, and they were interested in the influx rate of cosmic dust. In particular, they were looking for ferromagnetic spherules that are generated when material enters the Earth's atmosphere and ablates. And so they thought if they go to Barbados, they'll have nice steady winds, the winds will be clean, and they can separate the particles. Well, it turned out that they started exposing their samples, and they collected huge amounts of dust. This is the tower they built initially along the coast, and that's about almost 15 meters, I guess it was. It's on the east coast of Barbados, and over there somewhere. I have a bad view of that map over there, but I think you can see where it is. Why don't I have a better pointer here? Well, here's the pointer. It's a puny pointer, so it's right over here. And so they exposed meshes in the wind and the air blew through it, and the particles impacted on the mesh, and you can see there I am holding a mesh that's folded over, and within a matter of hours it'll develop that red-brown cast. You can actually see it on the one on the poles there, and you rinse them off, and you really have a layer of mud. And we have pounds of dust. Cassie may still have do you still have those in a closet? There are hundreds and hundreds of little vials with, and some of them have an inch of dust in them. So it gets an incredible amount of dust. And this is very convenient, particularly for crystallographic work, which we were doing at that time. We published a number of papers on that topic. And then there was no electrical power there, so that's why one of the reasons why they used the meshes. And I didn't have any funding for this sort of research. This is all bootleg. I had an O&R grant to look at bubble fractionation, that is the fractionation of seawater when you have a bubble erupts, the bubble collapses, and you get this jet drop, and this can lead to a composition that's different from bulk seawater. So I had money for that, but not for dust. But I thought the dust was more interesting. So I bootlegged the work in Barbados. We moved to Ragged Point, which is north of where the tower was, and these images show you the various stages. This is our original hut with the samplers en masse. There's me with a filter. Then we put up a fold-over tower, and then eventually we got to this point. Actually, this is not a recent photo, but that's Lillian Costals over there, marching off to work in the morning on a field trip. And in the upper right over here, you can see this is where the tower was originally, and this is where Ragged Point is. So the data. So this is the data from 65 to 2011, and the bars are annual mean dust concentrations, and the different colors refer to different publications. There was a review article that we did, and it's citations on the lower right corner, which has a lot of the history of this and just the general discussion of the so-called discovery of African dust transport in the Saharan air layer. But anyhow, so you see the annual mean concentrations, and it goes through very substantial changes over the course of the record. I mean, there's within each year there is a seasonal cycle, which you'll see more about shortly, but you can see that there is a coherent pattern. Overlain is a red line, which is the Sahel precipitation anomaly. That is, it's the deviation from a long-term mean, but the scale is inverted. So negative values on the right-hand side, the negative values at the top, the positive are at the bottom. And so you can see that the times when you have periods of several years of high dust concentrations, it's a period when there was less rainfall. That sounds logical, but strangely, the modeling community feels that winds are far more important. Well, I mean, there are a number of scenarios by which, I mean, when you have drought, a lot of meteorological conditions are changing, but it's very clear here that this is certainly one outstanding factor. So the other question was a shorter term variability, and at Barbados, you can see, if I showed you a day-to-day record there, you would see variations, but it's more clear when you look at devices which measure on a higher time resolution. This is a station on Martinique. Here's Barbados is the lower red arrow, and the other red arrow above it is Martinique, and they have an extensive collection of PM10, PM2.5 samplers. These are samplers that are used for air quality, establishing compliance with air quality standards, and they're TOMs. It's the same instrument that Cassie now has in Barbados, only recently installed there. But these are used all over the world. They're like 15, 20,000 around the world. So they're very convenient. And it turns out that 90% of the dust mass is PM10, that has an aerodynamic diameter less than 10 micrometers diameter. PM 2.5 is less than 2.5 micrometers diameter. And those standards are established that PM10 can penetrate your upper respiratory system efficiently, but PM2.5 is the one that can get down more efficiently to your lungs. But anyhow, what you see here is a large, when you get into the summer dust season, this large variation, which is cyclic, and if you look at the vertical bars, it's about the order of a week. And that's about the periodicity of easterly waves. So I became very soon, even though I didn't have this record, it was very clear in Barbados very soon that there was this periodicity which could be linked to easterly waves. And we all hear about easterly waves here in Miami, so that it gave me some inducement to look into it. This is also from the same island. It shows you a whole year of PM10, and you can see in the spring you get the noisy pattern, and then you break into the summer months and you get this half of the year you have African dust pulses coming into the Caribbean. So at this point, I met a fellow, Toby Carlson, who worked with NOAA at that Hurricane Research Division, which at that time was located in the Unger building, and also our proto-meteorology was located in the Unger building, Eric Kraus and Klaus Ruth. And but I met Toby completely by chance, and he was a meteorologist. He recently graduated from University College London in meteorology, and we immediately struck off a good correspondence of interest, and this led to a critical ad hoc experiment. There was a flight scheduled to Africa to measure radon in the atmosphere because NOAA had an interest in radon, and I won't go into that, but radon is a decay product of the radium decay series, well, the uranium-238 radium decay series, and you filter the aerosols, and when radon decays, it emits daughters that are radioactive, and they attach the aerosol, and you collect the aerosols. And so this is a flight from Barbados. Why am I not? Oh, I'm pressing the wrong button. That helps. Okay, so we start here in Barbados and we fly to Dakar, and 2 days later we return this way. So when you go across, these sketches are made by the flight meteorologist who was Neil Frank, who 3 years later would be head of the National Hurricane Center. But you can see as you go across, you have a nice towering cumulus, and then all of a sudden everything's suppressed, and that's when he begins to record haze. And the axis of the easterly wave is right around in here where the red line is shown. And on the return flight, you can see it very dramatically here as well. So there was a clear correspondence between the movement of easterly waves and dust, which is clearly associated also with meteorological processes over Africa, and African easterly jet, things of that nature. And this is what it looks like in the areas where you have dust. This actually is not on that flight, but it's something I just picked out of the files from the NOAA G4. So the next big thing, mind you that I have no money to do any research on all this at this point. So the next big thing, and the one which made my profession, was the BOMEX experiment, which is the Barbados Oceanic and Meteorological Experiment in 1969. That flight I showed you was late in '68. And so there's this research square here, and the idea is to carry out 3 months of flights. This was a prelude to the later GARP experiments, global experiments. So the idea was to monitor the heat, moisture, and momentum fluxes through this square. Barbados, you can see where Barbados is. So the flights would go around that square at different altitudes. And so I flew all 3 months, 32 flights, and 1,360 filters, and developed these profiles. And one of the vertical profiles I show you on the right there, and it shows that most of the dust, the main transport of dust, is in this layer, which tops out, in this case, in the mean at about 3.5 kilometers, but can go up 4, sometimes 5 kilometers in this region. And that layer is characterized as being very dry, very hot and dry. And this shows a vertical profile, which I can't read from here, but you see the temperature profile has a very sharp inversion, and the moisture profile, the water mixing ratio, drops dramatically, like 2 to 4 grams. I don't know, well, it depends where you are in the profile, but it's extremely dry, which is what you expect for an air mass coming off the African desert. In 2014, we're involved with an experiment in Barbados, which had a LiDAR on the plane, and those profiles on the left show different conditions, but the top profile shows the Saharan air layer, very clearly defined with respect to the boundary layer. So, and then the cartoon sort of depicts what goes on with this layer coming off Africa and slowly declining as it comes across, suppressed conditions initially, so that the dust concentrations are not rapidly removed by precipitation. And then as you get into disturbed areas, then the precipitation begins to take effect. So there's a lot of interest in the Saharan air layer from the standpoint of tropical disturbances and hurricanes. These are a couple of papers dealing with that subject, and Jason Dunyan wrote one of the first papers with Veldin on this topic, and there have been other papers. I have one below also dealing with that. It's a major topic today, but it's very poorly developed. But it's interesting that last summer, which had been predicted to have above normal number of, can someone get my coffee for me? Oh, thanks, Jim. So this past summer, the expectation was above normal number of tropical storms and hurricanes, and actually it was pretty dull. Late in the summer, I was getting emails from various people in the hurricane community asking, what's the situation with the dust? Is there unusual amounts of dust? It was not unusual amounts of dust. It's a complicated topic, and but it's still an open question. So let's go to the climate, longer-term climate. This shows the monthly mean Barbados record through 2017, and there you see the seasonal cycle. These are monthly means, and in the upper left there is a picked off some publication. I lost which one it was. There are a lot of them, but it shows the insert shows the major El Nino events. And if you go through that list of identified major El Nino events and compare with the dust record, and I mark those years with the red bar at the bottom, you see that there is some sort of correspondence between the El Nino La Nina sequence and the dust record. And recently there have been a couple of papers on the topic which look at that relationship between African easterly waves and ENSO. And one of these papers, the top one, is one of our local peoples involved with that one. And I'm not going to go through the papers, but in effect they see a relationship between El Nino sequence and African easterly waves, which obviously would have some sort of, you would expect it to have some sort of effect on the transport of dust. So at this time, in the 70s, I participated in the GATE experiment and in the Figge Atlantic Tropical experiment. And so in the late 70s, we had an opportunity to set up a sampler in French Guiana, because if you look at the seasonal cycle of dust, you expect there's a significant transport during the other parts of the year, but it would go south to the more southerly latitudes. So we shipped off a sampler. A graduate student was going to French Guiana, so we gave him the sampler, and we had people in French Guiana that were willing to set it up and operate it. So we got a couple of years of data, and we had this Nature paper showing the dust transport. This is the first paper ever showing the transport of African dust to South America. And there's been recent interest in this because of the possibility that this could play a significant role in supplying nutrients to the Amazon basin. And we've had some publications on that, and we've cooperated with other people looking at that as well. I don't think a lot gets deep into the Amazon because the ITCZ presents a problem across the region. But anyhow, so and we put up a sampler in KN eventually, and that's shown in the upper right. At the bottom, you should see the PM10 record is at KN, and that really clearly shows the seasonal cycling of African dust. And just to give you the perspective of where these various stations are located, at this time then we're doing Miami, Barbados, and KN. So we have the Saharan dust plume pretty well covered during the entire annual cycle. But in this figure, I take the long record for Barbados and the record of PM10 from KN and compare it to MIRA2, which is a modeling, a transport model, aerosol and gas transport model, which is not a forecast model. Most of the models you see talked about in the literature are forecast models because they want to be able to project into the future. But this one is a retrospective model. And it does an excellent job. You see in blue is the measured concentrations in KN, and Barbados in the red is the model. So it does a really excellent job. But it only does an excellent job from about 2000 when the MODIS satellite went up, because it assimilates MODIS. Well, it assimilates a lot of stuff, but amongst satellites, the most reliable and most frequent coverage is MODIS. It does an excellent job, and I use it a lot. But before 2000, when they only had AVHRR, it did not do a good job. It was pretty bad, in fact. So you can't use it retrospectively. You can't effectively use it retrospectively before the age of MODIS. That is, there was MODIS Aqua and MODIS Terra. There are two MODIS satellites which operate the equator crossing times that are several hours apart. So the next thing is broadening our network and our coverage. And the first thing that we did was the CIREX experiment. This was this was headed by Bob Deuce and me, and we in effect decided to divide the Pacific amongst us. The University of Rhode Island and people they cooperate with would carry out intensive field experiments at specific locations, and one of them was Anahuac. And we decided on doing the Pacific because there was data from the Atlantic, and we knew the Atlantic had a lot of continental impacts. So the question was, what's going on in the Pacific? The expectation was in Anahuac, which is, you can see where it is on the figure. I can't see it very effectively. But you would not expect, which has very strong easterly winds, you would not expect to get a strong impact from the continents. But in fact, they put up the tower, which is a very elaborate tower, as you can see. And then they started sampling, and immediately the filters turned sort of a yellowish color. And it was actually dust from China, which follow the trajectories that you see here. And there were two people from the lab here. John Merrill was in MPO, a meteorologist, and me, and then the other people were from the University of Rhode Island, and there were other collaborators with other aspects as well. So this was the first indication that there was substantial transport out of Asia, and of course, eventually we would see the impact of the pollutants, particularly the sulfates. We then proceeded to go through, set up stations all around the Pacific. This is in New Zealand on 90 Mile Beach, and this is one of the ships that was used. And we eventually set up a network of stations throughout the Pacific, and this shows actually all of our global stations. You can barely see the arrows, but we had 30-some stations eventually, but they were not all necessarily working at the same time. And here's some data set up to display the difference between the oceans. The red are the Atlantic stations. This is Iceland, Macehead, Bermuda, Miami, Barbados, Sal Island, and Palmer Station. No, Palmer Station. Yeah, I guess Palmer. Yeah, Palmer Station. The blue are the Pacific stations, and the green are Indian Ocean stations. And this is a log scale, so you can see a dramatic difference between the northern and southern Pacific Oceans. And this is for non-sea salt sulfate. You see the same general pattern. Again, that's a logarithmic scale. And of course, this is latitude here. And do that on a linear scale, and the change stands out much more dramatically. So it's all the Atlantic stations and a couple stations off the coast of, this is Korea, and this is, I forget where that is. But to show you the impact, regional impact seasonally, this is 3 southern ocean stations, Indian Ocean stations. This is non-sea salt sulfate and methane sulfonic acid, which of course is emitted, which is a oxidation product of DMS. And you can see that the sulfate in those regions is atmospheric sulfate aerosol completely dominated by oceanic sources. So then we moved to the Atlantic for a 10-year program under AEROS that was headed up by my group here in Miami. And I won't say too much about this. These are the dust concentrations, the monthly mean dust concentrations. And again, these are not all concurrent necessarily, but the scales are all very different. But note that Macehead has very low concentrations. Macehead samples the westerly winds here. And here is Iceland, which has high dust concentrations because Iceland turns out is a big source. We had a paper in Science showing that the proglacial deposits on Iceland are a strong source of particulate matter, and so there's a lot of interest in both what in the atmosphere. These are very heavy plumes of large particles get dropped out, but there are finer particles that would, of course, affect the radiative properties of the atmosphere, and also that would be deposited on ice and snow and would change the albedo of the ice and snow. If any of you attended the presentation by Lauren Zamora, she talked about some aspects of that sort of work. But really a dramatic, we had to set up a station on Hamay. Hamay is off the southeast coast of Iceland, and that's what the island looks like, and we were the little point. There's a little point up there somewhere, which is the lighthouse. We were at the lighthouse, and the other photo shows the lighthouse here, and there's 3 of us, the lighthouse keeper, me, and another person. But that's the device on the right is our sampler. And in 2008, I was presenting a seminar in outside of Reykjavik at the agricultural college, and at the end of the talk we raised the curtains and here was a dust storm moving down the valley over here. It was really a dust wall. It stands out. It doesn't stand out as well in the photograph. It's taken from the window, and this is the source. This is not on that specific day, but this is what it looks like. So there's now a great deal of interest in high latitude dust, and it's interesting that that there was a young student present, a young lady student present in the audience, undergraduate student who heard the talk, and she was interested, and she was a Czech lady, a young lady, and she went to graduate school, studied aerosols, came back to Iceland, and now heads a group studying high latitude dust, which has now become a rather hot topic. So spreading the word of dust to the high latitudes is my job, and she's doing the job of dust in high latitudes. Okay, I'm getting toward the end here. And the point I made earlier was when you look at models and what they use as sources, it's the only thing they have over the oceans is our stations. And this is a recent, relatively recent paper, just as an example, which lists all the stations. Most of the time they don't list the stations in a graphical way, they just have a listing. But all the stations except the three would have a crossover number are our stations. And the point is that when they're comparing these various models that are being developed, and all of them largely using our data for the oceans, there's a tremendous range of disparity. This is a global dust burden, and this is the MERA2, the model I showed you in the earlier slide, and this is the mean. Or I have it wrong. This is the black one is the MERA2. Yeah, black is MERA2. So there's a tremendous disparity amongst models. So my caution to any of you that is interested in ocean impact of deposition of dust to the ocean, you often see these papers and they pick a model and then they build up their whole story on the model. And an example of the disparities you can get into, this is a recent paper showing that the South Atlantic Ocean is getting 86 teragrams of dust per year, which is a third of what's in the North Atlantic. It's absolutely crazy. I mean, there's no way that there are no major dust sources in South America or Southern Africa that could do that. So, real problem with models. And this just compares a lot of models specifically with our data. The orange line is our data. And there are several pages of 21 different results. And this talks about the divergence between the models and the anticipated increase of aerosols, which they think they've been detecting otherwise, which I can't go into. So the wrap up is that I think that North Africa is the greatest source of dust on the globe, and we are the major direct recipients of African dust. So we're in a perfect location to look at the evolution of these African dust events and how they're modulated by weather and climate. Now we have a dust record, and I've shown you how we can see the modulation with ENSO, for example, and there are specific events driven by unusual meteorological conditions. But this, by setting up a network, if you will, of stations on the Western Atlantic, and there are a couple places along the Eastern Atlantic where there are efforts as well, and we have tried in an ad hoc way to coordinate with people in the Canary Islands, and we've done some papers with them. But I think there's a need for a more coordinated effort so that we can really characterize the evolution and time change in these air masses and the effects of those changes during transit. And there's the whole issue of impact on health. I tried to get the grants through EPA in the mid-1990s when they were first discussing set up standards. And I said, look, we have all this data from dust. We should look at the relationship between the PM10, PM2.5 standards and our dust work. I could not get any money out of it. I ended up writing papers anyhow, which are the first papers written on the challenges to the PM10 standards and PM2.5 with African dust. But I think that this is, a coherent. This could form the basis of a coherent, large-scale effort, which could be based in this school. We have the resources, we have the personnel, and we could do the job. So with that, I thank you.
So we have time for questions. Does anyone have any questions? All right, Amy.
Thanks so much, Joe. It's so really wonderful to hear the whole history of Erasmus woven in here. I wanted to ask you to try to go back to the 1960s version of yourself.
I would love to go back to the 1960s.
Let's all go back there. You couldn't have known what was going to, show up in the record. There's significant climate signals and decadal trends and interannual variability and stuff we didn't even really know about the atmosphere at the time that shows up in the records. And the way you told the story, it's there's a lot of dust in the ocean sediments and in the atmosphere and the tropical and the trade winds. And but I was wondering what you were thinking at the time, what was a science question that was driving you at the time?
Why is there so much dust and why does it vary?
Why do we need to know that?
Pardon?
Why is there so much dust? To do the Bob Ginsberg, so what? There's a lot of dust. What does it matter for? What was driving you then?
I hinted at it initially. There's the direct effects on incoming solar radiation, or outgoing long wave, not much, and on cloud microphysics, and that is a big part of the picture. And compared with other types of aerosols, dust is different in that there's a possibility of feedback loop, where if you have a period where you're getting increased dust, the increased dust can modulate the climate, which could either be a positive feedback, making conditions drier and windier to get more dust, or it could conceivably have a negative impact where it would lead to conditions with less dust. So, and that's a very, very complex picture, which they're still trying to sort out for aerosols in general. But it's the feedback which is different from the other aerosols that people worry about today. We know we put sulfate aerosols in the atmosphere. We put sulfate, nitrate, and other aerosols. We know where they're coming from, and we can do something about it. But the dust is a different matter. The source function of dust, I think, is the biggest problem by far, and that's where there's so many factors that modulate the source properties that I think that's where the models have their biggest problem. Once you put something in the atmosphere, meteorologists are pretty good at telling where it's going to go, but it's the source function is the big problem. So, but the time aspect, of course, with Emiliani, they used to have these seminars. I knew nothing about this. But Emiliani was the nucleus for a lot of seminars and meetings at the school, where you had paleoclimatologists, people working with ice cores, things of that nature, and ocean cores, and of course the sediment work that was being done here as well. The ocean core work that was being done here as well. It was a big thing. And so I became aware of the variability, particularly of dust and ice cores. But of course that's an entirely different time scale. And at that time, you know, now we have a better idea of what was going on. But I mean, that was just very curious, and without any good idea of what was driving it. So that was that sort of alerted me to the issue of variability and the factors that might be controlling it, and what, you know, I've been interested in ever since. But, you know, I know very little about paleoclimatology or meteorology or anything else. So I just collect samples and try to make sense of them.
Other questions, Ph.D.
Yeah, fascinating talk. I was curious if you think that the questions have changed now that we have good satellite data, so we know the aerosol optical depth pretty well. So do we need to refine the questions that are being posed at these surface sites, or just change them?
I mean, I have a little presentation. I mean, AeroNet has been phenomenal, and I had a role in AeroNet, and you know, I will take a minute. I actually have some photographs here, but some images. But I don't know, many of you probably don't know what AeroNet is. AeroNet is a NASA program, which is a federalized network of sun photometers, auto-tracking sun photometers. We measure the direct solar radiation in various passbands, and this instrument tracks the sun during the course of the day and makes other measurements. And from that, you can infer concentrations of aerosols and also characteristics of the aerosol, such as in a crude way, of size distribution. And so I was interested in sun photometers since the late 60s, when Fred Volz, who was sort of the father of sun photometers, was making these little handheld things. They were pretty crummy. So I wanted to put some on ships, and which would be dropped, and his instruments would break. So we designed our own sun photometers. Tom Snowden and I built sun photometers in a little box. I actually have one at home. I forgot to bring it. And we put these on the ships. It was terrible results because the people were not careful, and it was a little more difficult on ships. So in the late 80s, I was at a panel meeting at NASA, and Brent Holman had recently been hired, and Brent is the head of this would become the head of this particular group. And he was going to Africa, and he was interested in normalized difference vegetation index, which is very difficult to infer from satellites, particularly at that time, because you had to know the properties of the aerosols. So he wanted to set up a network of aerosols, but NASA wouldn't give him, will only give him 2 photometers. So I told him, I said, you know, I have 2 dozen sun photometers, you're welcome to them. So he took him to Africa, and he had a network of 14, 16 stations in the Sahel region, which is a critical region, both for the vegetation and also dust. And he wrote a paper in '91, and on the basis of the paper, he got money to buy photometers, but the CEMAL was coming out, that was just being produced. CEMAL is the automated photometer. We have one here. Ph.D. will be glad to take you up to show you our CEMAL. And on the basis of the paper and my sun photometers, he got a slug of money. His first group was 6 CEMAL photometers. So the AeroNet evolved from that. So today, if you go to the AeroNet site, you'll see there are about 500 sites around the world. And every paper that deals with aerosols, clouds, radiation, whatever, uses AeroNet. Holman has, I think it's over 1,000 papers. He has a name on huge number of papers, and he has 105,000 citations. Just because the ubiquity of and the necessity of the AeroNet readings. So I called him up to make sure I had my facts straight. So he sent a photometer back, the first one that Tom and I built, my 302, all beat up, still still apparently used. Well, you have to change the filters. But the 50-year-old photometer. If anyone wants to look at a 50-year-old photometer. But yeah, so that's that. It's the groundwork which is essential, and that's why people use our data. There's nothing else.
So you should bring it in and we'll display it somewhere in a library or some
Okay.
other spot.
Well,
That'd be cool.
I was thinking that it's a shame this school doesn't have a museum. I was Roland. You had asked about notable people, and one notable people was Roger Lermite, who invented Doppler radar. I mean, if you look him up on Wikipedia or anything else, he's the father of Doppler radar. And he was working on, when I was doing my initial aerosol sampling on the north wing over there, he had his little radar set on the roof of the north wing, and I would complain that he had all this traffic going back and forth that was stirring up the dust on the roof. So we would yammer one night. But I mean, he's famous, really famous.
Yeah, he was also a pioneer of Doppler sonar.
Yeah, well, I didn't know that so much. But
Yeah.
the
By the way.
Doppler radar certainly has had a tremendous impact. And yeah, there are a number of people. I mean, the remote sensing group here, the Ocean Color Group, Howard Gordon is a god in remote sensing in the 90s, the work they did. And it's his story has sort of gotten lost, well, Otis and Howard and the third guy, all of a sudden I can't think of his name. But they were really phenomenal. Maybe who was the other?
Bob Evans.
Bob Evans. Bob Evans is famous in a different light. He was the guy that really made the decision on Apollo 13. If you remember, Apollo 13 had a problem when they had an explosion which wiped out their power source. They moved into the LEM, and the question is, how long would the batteries last on the LEM? Those of you who were were old enough at that time to remember it, they were, all three of them were huddled in the landing unit, the small cramped landing unit, and they were running off batteries. There was only source of power. So they had two options for bringing them back. One, which was in effect to just try to turn it around on its path, and the other was to loop around the moon. And it all depended, and looping the moon was the safest, but it all depended on how long the battery would last, because there was super cold temperatures. So the authority on that was our guy here, and he told them, he had worked for a company that made the batteries, and he told them the batteries would last, given the facts he had about the power draw, and that was how the decision was made to go ahead with the mission the way it was carried out. When he retired, apparently NASA sent down a contingent of people to honor him. Yeah, there are a lot of interesting people around this camp and have been in the past.
Any other questions? Otherwise, we'll wrap up and thank Joe for an exciting presentation.